looked at the definition of controllability, and we looked at the condition for controllability, right? So in terms of forming the controllability matrix, and then essentially like looking at the rank of the controllability matrix. So in today's class, let's look at a few examples, right? We will also understand the workflow to be followed, like whenever you and I are analyzing systems for in this using the state space representation. So let's do a couple of examples, right, to understand that. Okay. So the first example, what we do is that like we consider a second order system. See, once again, we are considering a second order system because we won't get lost in the mathematics, right? So the mathematics will still be tractable enough, and we will still understand the concepts that you and I. That's the reason I am considering second order for our discussion. Essentially, we have the second order system where the state matrix is a diagonal matrix -1, 0, 0, and 2. And the input vector is 0. Okay. So this, if we recall, is a decoupled realization. We immediately see that the state matrix A is a diagonal matrix. So why do we say this is a decoupled realization? What was a decoupled realization? If you look at the two state equations, please note that the evolution of x1 depends on x1 alone, not on x2. Similarly, the evolution of x2 depends on x2 alone, right? Not on x1. Okay, so you can see that that's why it's called as a decoupled realization. Okay, so what we do is that like we look at the equilibrium state. So if we solve ax star to be equal to 0, what we do is that like we essentially solve for this equation to be equal to 0. When we solve that, we essentially get x1 star equal to 0 and x2 star equal to 0. Okay, so we get the equilibrium state as 0 and 0, or in other words, the origin becomes equal to the equilibrium state. Okay, now when we have the origin to be the equilibrium state, once we calculate the equilibrium state, we look at the stability of the equilibrium state. How do you and I determine the stability of the equilibrium state? We calculate the eigenvalues of the state matrix. So we solve determinant of A minus lambda I to be equal to 0. So once we solve that equation, we get lambda to be -1 and 2. Okay, so this is another advantage of decoupled realization with a diagonal matrix. So even the calculation of eigenvalues becomes very simple, right? When we calculate the determinant, it's just the product of these two terms, because the off-diagonal term product is 0, right? So the calculations become very simple. So the eigenvalues become -1 and 2. Now, why are we saying the equilibrium state is unstable? Why are we concluding that the
because eigenvalue, one of the eigenvalues is positive, sir.
Exactly, right? So you can see that for asymptotic stability, we need all the eigenvalues to be in the left of complex plane. But one of the eigenvalues is at +2, which is in the right of complex plane. Okay, so so essentially that's why it's unstable. Then what we do is that like we look at the controllability of the system, right? So when we want to evaluate the controllability of the system, we calculate the controllability matrix, which in this case is B and AB. Why are we starting at A? Why are we stopping at AB? Please note, for a nth order system, we go till A power n minus 1B. Okay, so for a second order system, n minus 1 is 1. Okay, so that's why we go only till A, B, and AB. Okay, so I hope it's clear, right? So the controllability matrix becomes B and AB. B is just 0, 1. Okay, that is the input vector. AB, we form the product of the matrix A with the vector B. So the matrix A is -1, 0, 0, 2. The vector B is 0 and 1. So AB product becomes 0 and 2. Okay, so we get the second column as 0 and 2. Now, if we look at the controllability matrix and calculate its rank, the rank of this matrix is 1. Okay, so it's a 2 by 2 matrix, right? This controllability matrix. How did I get the rank to be 1? Because you can see that if you take the two columns 0 and 1 and 0 and 2, I can write each other as a multiple of one another, right? I can write the vector 0 and 2, the column, as 2 times the column 0 and 1. So when you can rewrite columns in this way as a scalar multiple of other columns, the matrix is not of full rank. Okay, so the rank decreases. So another way in which people check whether a square matrix is full rank is by taking its determinant. Okay, so if the square n by n matrix has rank n, the determinant of the matrix is non-zero. But in this case, when you calculate the determinant, we get the determinant as 0. Okay, so that is why the rank is not 2. Okay, it is 1 in this case. So consequently, the system is not completely controllable. Okay, so we know that the necessary and sufficient condition for complete controllability, if you recall from the previous class, was that the controllability matrix should be of rank n. Okay, the rank of the controllability matrix should be n. Okay, but in this case, it is not n. Okay, n is 2, and the rank of the controllability matrix is 1. Okay, so what happens here? So how do we proceed in such problems? So the point is the following. When we now go back and relook at these two equations in a decoupled realization, right? X1 dot is minus X1. The solution to this equation is X1t equals X10 e power minus t. Okay, so you can immediately see that although this state X1 is not controllable, because I am not able to control it using U, the dynamics is stable. That means I start with any X1 0, which is not 0. The value of X1t tends to 0 as t tends to infinity. Okay, so that way it is stable but not controllable. On the other hand, if you look at the second state equation, X2 dot, it is 2x2 plus u. Okay, so you can immediately see that with this, the the solution will have a e power 2t term, which is what will blow the state to infinity. That is why the system is unstable, right? The equilibrium state is unstable. However, we can still stabilize the evolution of X2 by designing a controller such that you and I can give a control input for stabilizing the closed loop system. Okay, please remember, broadly, the purpose of control is to stabilize an unstable system to begin with or improve its performance, right? Or sometimes both. So in this particular case, the dynamics of X2 is unstable, but fortunately, X2 is controllable. Because why? U of t is appearing in the equation. Then what happens is that the dynamics of X2 is such that you and I can regulate the evolution of X2 and make it stable by designing an appropriate controller, okay, and giving it an appropriate control input U of t. Okay, so we can conclude that like X1 is stable but not controllable. What do we mean by that? Like X1, we can immediately see that the dynamics of X1 is such that X1, despite a non-zero initial condition, the value of X1t will tend to 0 as t tends to infinity. However, like X2, despite it being unstable, like it is not controllable. Okay, so that is the conclusion that you and I can draw from this example. And a system in which all uncontrollable states are stable is what is called as a stabilizable system. So this example that we consider is not completely controllable. Okay. Why? Because X1 was not controllable at all, right?
So just can I ask one thing, sir?
Yes, please.
You know,
Yes,
sir, if you
please.
go to the previous slide, sir, please. So you have told that x1 is stable but not controllable, right? Mathematically, since ut is not appearing in the first equation,
Ah,
so is that the reason behind that? What I mean to say, if I just
that-
wanted to look at
ah,
mathematically.
absolutely, Roshan. I know we'll answer this question in the next 10 minutes, okay?
Okay, fine.
Because I am purposefully constructing examples. And in the next example, you will see that that is in fact not necessary, okay? We will also understand why it is the case, okay? So then I will make a subtle connection between this conclusion which I am drawing. This is whatever, since you have asked this question, let me preemptively answer that. This is true only when you and I do not have a or have a decoupled realization. What do we mean by decoupled realization? What to say? The evolution of every state variable depends only on itself, okay, not on other state variables. In other words, the consequence is that the state matrix is a diagonal matrix, okay? So that only then you and I can make such conclusions. However, in the next example, we will see something interesting. Okay, so please bear with me for another 10 minutes, then we'll come back to this. Yeah.
Sure, sir. Thank you.
So yeah, in this example, the system is not completely controllable, but like the uncontrollable state x1 is stable. Okay, so consequently, we have something called as a stabilizable system. Okay, so in state space representation, when we want to design controllers, ideally you and I want a controllable system. Okay, but in case you and I are not able to get that for a particular system, we at least want a stabilizable system. Okay, so that is what we need at the bare minimum. All right. Okay. So that is the definition of what is called as a stabilizable system. Okay. Now let's look at this example. Okay. So we consider example 2, wherein the state equation is this. Now, what is the difference between the first example and the second example?
It has the third, like what a third, like in diagonal was 0, 3 is appearing over here. Like
Exactly.
2
Right.
2 is,
What?
yeah,
Yeah.
1 2 is
Exactly.
there. 1 2 element is there.
Exactly, Roshan. Like what I have circled and what I just marked in arrow, right? This off diagonal element, which was previously 0, has now become 3. Okay, that is the only change. Okay, so the other elements are all the same. Still, the value of n is 2. Let's go through the same exercise. Okay, so this should be a standard practice for all of us, right? When we design controllers using the state space representation. First, we calculate a x star to be 0. By now, we should know how we got x star to be 0, right? Because the state matrix is invertible. Okay. Then what we do is that we essentially calculate determinant of a minus lambda I to be equal to 0. When we do this, and then we calculate the determinant and then process it, we still get lambda to be minus 1. Okay. So you can see that still there is one eigenvalue in the right of complex plane. The equilibrium state is unstable. Okay, no doubt about it. But now, what changes? We observe something very interesting. Okay, we calculate the controllability matrix CC, which is once again B and AB. Now you can see that B is 0, 1. When we calculate AB, due to the fact that this off diagonal term is now non-zero, AB comes to be 3 and 2. And the controllability matrix now has full rank. So if you calculate the rank of this matrix, it's 2, because now you cannot express one column as a multiple of the other, right? And if you calculate the determinant, it comes to be minus 3. So when you have once again a square matrix of dimension n, if the determinant is not 0, then the rank of the matrix is n. Okay, so that is the conclusion, okay, that you and I can draw. So consequently, the rank of the controllability matrix is 2. It is of full rank. So it is completely controllable. So we can see something very interesting happening here, right? So let's rewrite the two state equations one by one. The first state equation will be is now x1 dot equals minus x1 plus 3x2. x2 dot is 2x2 plus u. The second state equation remains the same, right, as before. Okay. What has changed? The first state equation has changed. And now we can see that this is a coupled realization. Okay. So what you and I have figured out is that both states are controllable, right? Because the controllability matrix is full rank. So the system is completely controlled. When we say completely controllable, all the system states can be controlled using the well-designed control input. But you and I may ask the question, hey, in this equation for x1 dot, where is u? Correct? A natural question may come. Then why do you think now suddenly the state x1 has become controllable while previously it was not?
Because x2 is being controlled by ut, and hence
Ah.
x1 will get controlled by x2 in that sense. So ut is
So,
controlling both x1 and x2 indirectly.
exactly, right? See, you can see a direct impact of control on x2, okay, through the second equation, okay? That doesn't mean x1 is not controlled by u. x1 is being controlled by u through x2, okay? So it's an indirect connection, but it is there, okay? So this is what we need to be careful about, okay? So I hope, Roshan, now coming back to your question, when we did not have u of t explicitly appearing in a state equation, the question that you and I need to ask is that, like, are we dealing with a decoupled realization or a coupled realization? Only in decoupled realization, we need u of t to appear in all the state equations for complete controllability. When you have coupled realization, that means the state matrix is not a diagonal matrix. We need to evaluate the controllability matrix to comment on complete controllability. Okay, so u of t need not explicitly appear in all individual state equations in a coupled realization. Okay, so the input can influence other states indirectly. Okay, so through the states in which it appears explicitly in the corresponding equation. I hope that clarifies your question, right?
Thank you, sir. Yeah, sure, sir.
Yeah. So what we have understood from these two examples are multiple things. That is, when we are given, a particular, state space realization, what we first do is that, we calculate the equilibrium state, we calculate the eigenvalue of the state matrix, we comment on the stability of the equilibrium state, and then what we do is that, we look at the controllability by calculating the controllability matrix, and then we go for controller design. Okay, so I hope the process flow is clear. Okay. Any questions on how we evaluate controllability using the controllability matrix?
Just one question, sir. Suppose we calculate the eigenvalue of this system, and both the eigenvalues are negative in that sense, right, sir? That means the system is stable, and if the system is stable, we did not to find the controllability of that, right, sir? Because it will be controllable, right?
No. Stability does not imply controllability, Roshan. Okay. See, for example, let's take a very simple example, right? Even let's say if I had this element to be -2, what will happen? The eigenvalues will be -1 and -2, right? Equilibrium state is stable, but then x1 is still not controllable. Okay. Yeah. So stability is something, controllability is another concept. Okay. Yeah.
Oh, thank you, sir. Thank you.
But why are we looking at this? Because as we keep repeating, why am I designing a control system in the first place? Right? We are designing a control system in the first place because we essentially want, either to stabilize an unstable system to begin with, point number one, or second point is that we are given a stable system to begin with, but we want to improve its performance. Okay, under both scenarios, we design controls. I hope that clarifies, right?
Yeah, perfectly right, sir.
Yeah.
Sir, one question I want to ask you. I'm sorry to just poke in that way,
Uh.
sir. Probably while like doing project and all those things, we come across like CFD and all.
Mm.
what I mean to say, conjugate heat transfer and analysis, which typically but they're using a lot of mathematical, I would say, tool in that sense. And if you read the paper, there are a lot of same terminologies coming, coupled equations and all, like air side and metal side. Equations are being coupled and then it is being solved. So is the same concept is being used over there also? Just a
So, yeah, see, the word coupled, Roshan, can have different connotations. Okay. So, see, even in vehicle dynamics, we talked about coupled dynamics, right? So, where let's say you and I want to study the effect of a vehicle response under, let's say, a scenario like combined cornering and braking. Okay. So, what I'm trying to convey is that the adjective coupled depends on the usage of the verb. Okay. So, even in CFD and heat transfer that you're talking about, coupled equations typically may have to do with coupled physical phenomena, right? That the model is steady. Okay. So in this particular case, the way you and I have used the adjective coupled, okay, in this discussion, okay, I'm drawing a boundary for our discussion today, right? Is that when we call a state space relationship as a couple, what you and I are telling is that the evolution of a state variable is not only dependent on itself, but also on other state variables. That's what we can observe here, right? That is, if you look at the evolution of x1, which is x1 dot, it is dependent on x1, but it is also dependent on x2, right? That is why it is a coupled relationship. I hope that provides clarity, right? So,
thanks, sir.
yeah. Okay. So another important concept that I want to convey to you in today's class, if you recall, when we first started state space representation, I mentioned that there are some important canonical forms, right? Canonical forms are standard forms which we utilize, right, to study the state space representation and do analysis in a very constructive manner. Okay, so let's say we consider a third order system, right, which is constructed like this, right, without loss of generality, y triple dot t plus a1 y double dot t plus a2 y dot t plus a3 t equals b1 u double dot t plus b2 u dot t plus b3 u. Okay, so when you take the Laplace transform and calculate the transfer function, we get the transfer function as b1s squared plus b2s plus b3 divided by s cube plus a1s squared plus a2s plus b3. Okay, so I think this all of us are familiar, right? How we get. So the value of n is 3. It's a third order system. Okay, of course, I could have written the controller canonical form for a nth order system, but I'm just writing for a second and a third order system. Okay, considering the scope of our course. I'm not deriving this, but then we are just going to write this. Okay, so given this state equation, the controller canonical form is this. Okay, so you need to write this third order state space representation where the state matrix is written in this way. So how is the state matrix written? We write 1 in the first super diagonal term. Super diagonal means the term immediately above the diagonal immediately above the main diagonal. Okay, that's what is called super diagonal. Okay, so the first super diagonal has 1, and in the last row, what we do is that we write these coefficients of the terms involved in the governing equation in the reverse order, but multiplying them with a minus sign. Okay, so we last row starts with minus a3, which is the coefficient of y. Then we write minus a2, which is the coefficient of y dot, and then minus a1. Okay, so of course we go in this order and then write the last row. And the input vector is always this. Okay, it will have zeros all the way till the last term, which will be a 1. Okay, that's how the input vector is. And in the output equation, the output vector is written in this way. Okay, so for that we look at the right hand side, and then like we start from b3 we go from B3, B2, B1. Okay, so which are the coefficients of U, U dot and U1 double dot. Okay, of course, now without the minus sign. Okay, we don't multiply by minus sign here. This is what is called the controller canonical form. Okay, this is one way to write the state space representation. If you recall, when we looked at state space, what to say, representation to be like infinity, right? So there can be infinite number of state space representations, right? So this is one such state space representation, which is called as a controller canonical form. We'll see why it is useful, right? As we go forward and try to design controllers, okay, using state space representation. All right. Okay. So this is what we have. Okay. So as the controller canonical form, given this state matrix input vector and output vector in this form, we'll see that the design of the full state feedback controller, which we'll learn next, becomes quite easy. Okay. So that is the advantage of the controller. Let's do the same example for same exercise for a second order system. Okay. So now we consider a second order system for which the governing equation, general governing equation is this, right? And the transfer function is written as B1s plus B2 divided by S squared plus A1s plus A2. Now, how do we write the controller canonical form? This is a second order system. There are two state equations. The state matrix is a 2 by 2 matrix. So the off diagonal term, the super diagonal term, we write as 1. And then what do? The last row, we go the coefficients of the terms involving the output and the derivative from the right, but we multiply by minus 1. So we first write minus A2, then we write minus A1. Okay, so that's what we see in the last row. And the input vector, the first, all the elements till the last element is 0. Here we have only 2 elements, so that's why the second element is 1. Okay, the first element is 0. And then how do we fill up the output vector? We look at the coefficients multiplying the input term and the derivatives. We start from the rightmost side. We don't multiply by minus 1. We write B2 and B1. Okay, so that is the output vector. Okay, right. So this is how the state space representation is set up. Okay. Now, the point is this is the state space representation, and like this is the state space representation in the controller color. Just to demonstrate it, we can consider the mass spring damper system, where we know that the governing equation is this, right? Mx double dot plus Cx dot plus Kx equals F. N is equal to 2. And the plant transfer function is 1 by ms squared plus Cs plus K. All of us know about these things. Now, we put it to the standard form. Standard form means the value of the highest order of the output term, derivative term is 1. So we derive 2 by m. So we get it in this form, right? X double dot plus C by m x dot plus K by m x is equal to 1 by m f. Now, if we compare it to this equation, right, this particular second order equation, you can immediately see that A1 is C by m, A2 is K by m, B1 is 0, B2 is 1 by m, right? So we can immediately write down the values of these 4 parameters. And then using that, we calculate or we write down the controller canonical form. As we discussed, it's a state matrix, a 2 by 2 matrix. In the first row, the off diagonal term is 1. In the second row, we start from the right, but then each coefficient we multiply by minus 1. Okay, so we have minus K by m and minus C by m. And then the input term, we have 0 all the way, we go to 1. Okay, so that's what comes as the input vector. Then what happens in the output vector? We start from the rightmost side. We go B2 and B1. B2 is 1 by m, P1 is 0. Okay, so the notation. If you can calculate P of S, right, using that equation that we derived, C dot Si minus A inverse B plus D. Okay, So then, you will see that you will get the same controller transfer function, plant transfer function 1 by ms squared plus cs plus k, right? And if you recall, previously when we started the state space representation, you can check in your notes, right? This is what you and I would have derived as a state space representation. Immediately we can see that the state space representation is not unique. Why? Because although the state matrix is the same, the input vector and the output vector are different now, right? In the controller canonical form, right? That can be easily observed by all of us, right? So you can see that the input vector is different, the output vector is also different, right? So the state space representation is non-unique. All right. So I hope that clarifies the controller canonical form. Once again, why are we studying the controller canonical form? The advantage will become very clear when we do the control design using what is called full state feedback, okay, which we will start learning from tomorrow. Okay. So, so these are the two important concepts that I wanted to communicate today. So what are the two important concepts? One is essentially, calculating or given a state space representation following a methodical process, wherein, we have, calculation of equilibrium state, then the eigenvalues of the state matrix that leads us to comment on the stability of the equilibrium state. And then followed by that calculation of evaluation of controllability. Okay, so those are the three calculations that we have done. And then we saw what is called a decoupled realization, what is a coupled realization, and what is their impact, right, on the controllability. Right, for a decoupled realization, we have a diagonal state matrix, and if the input does not appear in one of the state equations, then we know that it's not completely controllable. Okay, so those are the inferences that you and I can do. Okay. Now, the point is, we also looked at the controller canonical form, where we did not derive the controller canonical form. But then, what we did was that, given a standard governing equation, you and I learned how to write the controller canonical form for second order and third order systems. Of course, this could be generalized to an nth order system. Okay, but in this course, we are going to look at predominantly second order systems and maybe third order systems. Okay? So that's why I took those two specific cases and then wrote the controller. Okay, so tomorrow's class we'll come here and then we will look at what is called full state feedback. Okay, so where we will start putting together all the concepts that we learn and then figure out how to derive or design a controller using the state space representation. Okay, that's something we learn tomorrow. We look at a design example, and then we look at something called as observability, and that will lead us to the close of the theoretical part of this course. Okay, so we may need another 3 lectures to complete the theory part of this course. Okay, yeah. Okay. Okay. So any questions on what we learned today? No.
Sir, am I audible?
Yes, please.
So typically, we would want to decouple our systems, but mostly coupled systems are only controllable.
No, I think Prem, let me re-articulate my statement. Okay. See, in as far as physical phenomena is concerned, you may have coupled dynamics. Okay. The
Yeah.
physics may be coupled. What do I mean by that? Let us say you may be steering a car, also braking. Let us say you write the state space representation for that phenomenon. The base state space representation may have coupled equations. Okay. But you can always apply state transformations to decouple the state space representation in some arbitrary, choice of state variable. It may not even have physical meaning. But controllability is a physical property of the system. Okay, it doesn't matter whether you do transformations to make the state matrix diagonal or it remains non-diagonal. It's an inherent property of the system. Okay, you and I can change controllability just by doing transformation. we can study controllability by doing transformations. Okay, but then a system is either completely controllable or not completely controllable. Okay, transformation is not going to change it. Okay.
So majorly coupling and decoupling doesn't influence it.
No, coupling and decoupling. I just wanted to give you an intuitive feel about this. Okay, so please look at it from that perspective. Okay, why did I introduce this? I could have taught you controllability without even getting into coupled and decoupled.
Yeah, that is understood.
But I wanted to give you an intuitive idea of what is this controllability. That is, ultimately, you should be in a position to control the evolution of each state variable. Okay, by designing an input U. Okay, so then only the system is said to be completely controllable. Okay, in the jargon, they will just use controllable. No one will say completely controllable because it's understood that when you say a system is controllable, it means complete control. Okay, so that is point number one. Now, just to motivate that, I used decoupled and coupled realization. That's about it. Okay, if you use a decoupled realization, the fact that if you don't have U explicitly appearing, all the state equation means that it's not completely controllable. But it's not the case in a coupled realization. A coupled realization, you can control all the states even if U of T explicitly appears only in a few equations, okay, few state equations, because the dynamics of the states are coupled. Okay, yeah. I wanted to give that intuitive feel for it. Okay? That is the choice, that is the motivation behind choosing the simple second order equation. Okay? Yeah.
Got it, sir. But mostly coupling is bad. I mean, it's difficult to control, right? But we try to decouple in most of our controller designs.
Oh, okay. I would like to put it a little bit differently, Prem. I won't say coupling is bad. Okay, either we have controllability or we don't have controllability. Okay, please let's look at it from that perspective. Okay, but then the point is either we have controllability or we don't have controllability. Okay, so that is all I would like to say, right? Coupling and decoupling, it's a matter of convenience. Okay, if we are able to decouple a state space realization, the computation becomes simpler. Why? You and I get a diagonal matrix. Okay, then what happens when you get a diagonal matrix? What happens to the the inverse of a diagonal matrix? See, if you have a diagonal matrix thing, if I want to calculate the inverse of a diagonal matrix, right? What is its inverse?
Reciprocal only.
It is only the inverses of the individual elements. Okay, that's it. Okay, so what I'm trying to convey is that the computations become simpler, right? When you have decoupled realization, doesn't mean that you and I always need to have that. Okay, so that is the implication. Okay, so I hope I clarified from that perspective.
Yeah, that is
so. So I won't conclude that one is better or desirable or something like that. If you are able to find a decoupled realization by doing appropriate transformations, calculations will become simpler. Okay, but just by applying a transformation and you convert to a decoupled realization is not going to change whether a system is controllable or not. Okay, a system is controllable is an inherent property. Okay, just like a system is stable, right? A system is either controllable or it is not. Okay, that's it. Okay, so decoupled and coupled realizations are not going to change it. All right. Is it clear, Frank?
Yeah, got it. Just one more follow-up. The methodology that we have seen right now, or the concept that is applicable to LTI alone, or even for non-linearity also, will have the same relationship.
This is only for LTI. Okay, all these criteria. Okay, yeah.
Okay.
All right. So non-linearity, the definition is valid, but then what is the criteria is something as a different volume.
Yeah. Got it. Okay.
Yeah. See, the definition of stability is what it is, right? So that is You perturb a system, whether it comes back to the equilibrium state is same for non-linear and linear systems. But for LTA systems, we converted the definition to a criteria on the eigenvalues of the state matrices. Okay. So similarly, the notion of controllability is what it is. We wrote down a nice criteria for LTA systems. Things become complex if you go to non-linear systems. That's all it is.
Okay, sir. Okay. Maybe it might be more than these eigenvalues. It's something other might also come.
So yeah, because you don't have state matrix and all in non-linear system, right? So,
yeah.
Okay. Yeah.
Thank you.
Sir, it's not a question; it's a request, sir. Basically, sir, the second part of the course, which is based on state space equations and modern, I would say, control system. Sir, if you can get some what I mean, question to practice for the exam, because the concepts are really unique, and because while we are discussing with each other, what could be the probable questions, and what I mean to say is, in what way the question can be asked in that sense. So most of us.
I'm going to give you a homework problem, Roshan. I think by and large, if you practice that should help you with the exam preparations. Okay, yeah.
Okay, sir. Fine, sir. No problems.
So thanks. The one last homework, I think that should be homework number 5, right? Yeah, correct, Roshan? No, so that should help you to practice also. Okay, yeah.
Fine, sir. Thank you, sir. Thank you so much, sir.
But then how do we solve the non-LTA systems if we cannot use state space?
Yeah. So yes, for that we need to learn a course on nonlinear systems, right? So what happens is that there are something called methods of Lyapunov. Okay, so essentially we can apply those methods and then design controllers for nonlinear. Okay? So typically that is taught as a separate course. So in most traditional courses globally, state space is taught using the LTI, considering the LTI.
Sir, am I audible?
Yes, please.
This is not related to what Keshav was asking, but just to understand state space better, can we have one example from your side wherein we develop the state space model from a physical system, for example, some rotating mechanical system or something like that? Can we do an example in the class?
Yeah, exactly. That's going to be project number 2, right? So, exactly. Right. So, project number 2, Prem, is you will consider the cornering steering phenomena, and then from the governing equation you write down the state space representation. See what we did for the master damper system. Same thing you will do for the project.
Okay, sir. So actually we will put the body diagram, equations, and then we'll compose it.
Yeah. You will go through the entire process, right? So,
okay. Then got it. Yeah.
Right. So the reason I have structured this project is because it's very difficult to do it in one single class, right? And some things we need to do it by ourselves to learn. Okay. So that is why I have given it as a project. Okay?
Got it, sir. Apologies. Yeah.
No, I think these are valid questions, because I would have these questions when, we study. And in fact, the way I learned this modern control theory is also slightly unique and strange. In fact, see, if you recall, I would have taught you transfer function before I went to state space, right? So when I went to the US for my master's and PhD, I learned state space first and then transfer function. I went in the opposite sequence. That is hardly done globally. That is because in 90s and all, in mechanical engineering degrees, there was no course on controls, right? Now control systems is introduced, but I'm talking about nearly 30 years ago, right? So there was no course on control systems. So I didn't have a clue about transfer functions and PID and so on. But anyway, I went and took advanced courses where I learned state space first. Then I came and learned control transfer functions on my own because I had to learn, right? Otherwise, I could not cope up, right? I could not understand. So I understand challenges also because this will also look new to us, right? And we might have done so many quote unquote problems as in the previous case, right? Yeah. So that's why, like I'm going to give you one homework problem, and also the project will help you to essentially learn a little bit. Okay. Yeah.
Thank you so much.
Thank you, sir.
All right. Okay. So now, sir, is everyone present today? No, sir.
Yes, sir. Everybody is present, sir.
Okay. So I'll mark attendance for everyone. Then we will continue tomorrow. I think we may require 3 more lectures. We will continue tomorrow, but next Monday and Tuesday, I have to coordinate the peer review in my department, right? I set out the department, I need to be available. So it is very likely that we will not have classes next Monday and Tuesday. So after tomorrow, we will meet only next Wednesday. Okay.
Right,
So,
sir.
So if there is any change in that, I will let you know. But as of today, that will be our plan. Okay.
Okay, sir.
Okay, sir.
Thank you, sir.
Thank you, sir.
Thank you all. We'll meet tomorrow then.
Thank you so much, sir.